Hello, I'm Laura Marshall.
And I'm Melinda Rose, and this is Light Matters for July 31st, 2013.
On today's show, a laser-controlled switch turns blood clotting on and off. Plasmonics gives a performance boost to polymer LEDs and solar cells. A new 3D display doesn't disturb 2D viewers. And solar steam sterilizes with sunlight.
Researchers at MIT Lincoln Lab have successfully turned clotting on and off in blood samples using laser-controlled gold nanoparticles. The technique could help control blood clotting in surgical patients or promote wound healing. Blood clotting is produced by a long cascade of protein interactions culminating in fibrin, a protein that seals wounds. Blood-thinning drugs reduce clotting, but reversing the effects is challenging. Fibrin is formed from fibrinogen, a reaction mediated by the enzyme thrombin. Scientists previously found that a specific DNA sequence inhibits thrombin by blocking its binding site with fibrinogen. A complementary sequence can shut down the inhibition. The researchers had previously shown that gold nanorods can be designed to release compounds when activated with IR light. The size of the nanorod determines the activation wavelength, so two rods of different lengths can carry different payloads and be controlled separately. To manipulate blood clotting, they loaded a 35 nanometer long gold nanorod with the DNA thrombin inhibitor and a 60 nanometer long particle with the complementary DNA strand. To load enough DNA onto each particle, they exploited a side effect of nanoparticle biology, which is that particles attract a halo of proteins that bind to gold and get sticky. They soaked the nanorods in a solution of human serum protein and the DNA molecules, which allowed them to attach 6 times more DNA to the nanorods than without the extra proteins. When the nanorods are exposed to IR light, the electrons within the gold become excited and generate so much heat that they melt slightly, releasing the DNA. The process was tested on blood donated to hospitals, and the particles successfully turned clotting off and on in all samples. The research appeared in PLOS One.
A new plasmonic material boosts the performance of polymer LEDs and polymer solar cells while keeping their structures simple. Organic semiconductor devices are cheaper to make than inorganic ones, but further improvements in efficiency are needed before there can be widespread commercialization. Plasmonic nanoparticles can boost efficiency, but the contrary demands of polymer LEDs, or PLEDs, and polymer solar cells, or PSCs, mean that there are few metal nanoparticles that can enhance the performance in both. But a new material based on carbon dot-supported silver nanoparticles, prepared at Ulsan National Institute of Science and Technology in South Korea in collaboration with Chungnam and Pusan National Universities, is easy to synthesize with basic equipment and is low-temperature solution processable, enabling roll-to-roll mass production techniques suitable for printed electronic devices. The team demonstrated PLEDs with high current efficiency and luminous efficiency, and PSCs with enhanced power conversion efficiency and internal quantum efficiency. In fact, the luminous efficiency and internal quantum efficiency are among the highest values reported to date in fluorescent PLEDs and PSCs, respectively. The approach could lead to electrically driven polymer lasers. The work appeared in Nature Photonics.
3D glasses can be a pain on the eyes, but take them off and you're stuck staring at a blurry image. Now a 3D plus 2D TV display could change that. The new display, developed at the University of California, Santa Cruz, overcomes the typical 3D ghosting effect by showing separate left and right images when viewed through glasses. But without the glasses, only the left image is visible because a third image, a negative of the right image, cancels it out. The prototype was built by aligning a 3D projector with a second polarized projector that projects the negative of the right image. The LCD active shutter glasses are synchronized to the 3D projector to cancel out that negative image. 2D viewers see a low contrast image because the prototype makes the darkest pixel relatively bright. To restore acceptable contrast to non-glasses wearing viewers, the investigators enabled the images seen by the left and right eyes of the glasses wearers to have unequal brightness, where the left becomes brighter and the right dimmer. Experiments were conducted to determine the optimal brightness ratio between the left and the right images. A patent application has been filed, and a graduate student at UC Santa Cruz is now working with students at Stanford University's Graduate School of Business to start a company based on the technology. The work was published in ACM Transactions on Graphics and presented at SIGGRAPH 2013.
A new solar steam sterilization system uses light-harvesting nanoparticles to convert as much as 80% of sunlight energy into germ-killing heat, and it could be a boon for more than 2.5 billion people around the world who lack adequate sanitation. Sterilization and sanitation are enormous obstacles without reliable electricity, and solar steam opens up possibilities for off-grid sterilization that are not yet available, according to Rice University's Naomi Halas.
So this is a radically new way to harvest solar energy and to use it in a very, very general way. We're boiling water in a radically different way. We're taking sunlight and nanoparticles that absorb the solar spectrum, and we shine light on the nanoparticles immersed in water. They will absorb the light and convert the light to heat. We've used metallic particles, and we've also used conductive carbon particles. What's important is that the particles absorb light across the solar spectrum. And we demonstrated that in a video where we actually show, we start with the water with nanoparticles inside, and we sit it in an ice bath. We shine light on the nanoparticles, and they heat up and they produce steam even though the water in the solution is at the freezing point. Between 80 and 90% of the energy that's absorbed from the sun is actually converted to steam by the nanoparticles in this process. From the initial very small-scale lab experiments that we did outdoors, we've now, with the support of the Bill and Melinda Gates Foundation, we've been able to build the solar collectors like this and several other geometries that allow us to really build a platform that might, for example, serve the sanitation needs of an entire family.
The team hopes to work with waste treatment company Sanovation to conduct the first field tests of their waste sterilizer at 3 sites in Kenya. The work appeared in the Proceedings of the National Academy of Sciences Early Edition.
That's it for this edition of Light Matters, the Photonics Industry's only weekly newscast.
As always, you can write to us with your comments or questions at lightmatters@photonics.com.
Thanks for watching, and we'll see you next week.